Well, hello, hello. We have a little more chemistry to cover this week. We are going to finish up this chapter, Unit 9 on bonding today. And this will serve as pretty much Thursday and Fridays. Pretty much mostly Thursday. Friday, you could consider, if you watch all of this in one day, Thursday, you can consider Friday. You have all the time to work on the chemistry homework, and the homework's due at the end of the day. Let me also point out that that means on Monday, you'll be taking your first at home chemistry quiz. And then later that week, you'll be taking your test, likely on Wednesday. And I'll let you know how that's going to work out, taking it home. Anyway, back to chemistry and bonding. We just to recap yesterday, really quickly, we talked about polarity, and this is going into the next couple chapters a really big deal. To know whether a molecule is polar tells you so much about it, from relative melting and boiling points, surface tension, reactivity, how likely the substances will mix. And so we need to be able to quickly tell, yep, that's polar, or no, that is not. And so the first thing we said we need to look for is polar bonds. So, for example, down here we have carbon and oxygen. Since oxygen is more electronegative than carbon, then it is polar. This bond is polar. We have electron density being pulled to the left away from this carbon. And remember, the closer an element is to fluorine, the more electronegative it is. And so the difference between the two tells us that it's polar. So if they're very different, then it's very polar. But if it's just a tiny difference in electronegativity, then it's very only minorly polar. So again, a polar bond is when you have electrons unequally shared. Now, what we need to remember is from VSEPR and bond symmetry is that these polar bonds can cancel. So if you have two polar bonds going in the exact opposite direction because it's highly symmetric, they cancel out. So carbon dioxide is completely nonpolar despite it having two polar bonds. Now, in contrast, take a look at ammonia. It's got three polar bonds, but because it's trigonal pyramidal, they're all generally going towards the nitrogen. So nitrogen's kind of hogging all this electron density, making it polar. Whereas boron trifluoride, it is trigonal planar. So because it's flat, electrons are getting pulled in every opposite direction, 120 degrees, and this is a good picture of nonpolar. So there is no one place where electron densities migrated towards, whereas over here it's electronegative and electropositive. So again, this in the next couple of chapters we'll need to be able to tell whether it's polar or not. So today we're going to look at a couple different distinctions for bonding. So first, if we have single bonds, so we have one pair of electrons being shared between these two carbons. This is ethane. There's a little bit more detail I want you to know. So first off, if you only have one set of electrons being shared, they're shared directly in between. I mean, this should make sense. Now, over here, you're seeing this diagram of the orbitals overlapping, and so that's what's going on. So this is called a sigma bond. So it's kind of like what you'd expect. If you're going to walk up to someone, you might shake their hand. Your hands are directly between you and that person, not above you or below you or behind you or anything else weird. It's just directly between. Now, with this overlap, it allows for a freedom of rotation. So if you can see in this animation, it is free to rotate round and round and round and round. And that's going to be pretty significant. We'll talk about when it's not able to rotate in just a moment. But since ethane has 7 total single bonds, you could also say it has 7 sigma bonds where they're all overlapping directly between. Now, probably the biggest consequence of this rotation is when we draw Lewis structures, you might sort of think you're drawing something different when you're not. So if you look at these two, this is 1,2-difluoroethane. And over here is 1,2-difluoroethane. Again, you might look at these fluorines and say, well, these are really close. But over here, it's exactly on opposite sides. So they look like they're different. But because these bonds in the middle are single, they're able to rotate all the way. Okay, here I have these 3D model of that's showing the tetrahedral arrangement around the carbon. So each carbon has 1, 2, 3, 4 things attached. This carbon has 1, 2, 3, 4. So it's tetrahedral. All these bond angles are the same. But because this is a single bond, again, there's this freedom of rotation. So it doesn't necessarily have to be here or there. And so we could make it look like this one over here, or we could flip it and make it look like the one on this side. But they're technically the exact same thing. And so even though in 2 dimensions it might look like they're different isomers, they are the same. Now, things change when you introduce a double bond. So we know that with a double bond, it's a second pair of electrons. So there are 4 total electrons being shared between these 2 carbons. This is ethylene. So now what's really happening is, first, there is another sigma bond. Again, there's that handshake directly between the first pair of electrons, or just still going right between the 2 atoms. That is a sigma bond. But what makes the double bond unique is then the second pair of electrons, they make up what's called a pi bond. And pi bonds do not directly converge in the middle. Instead, it occurs in a plane. So here's the plane between the 2 atoms, above and below where the plane of where the nuclei are. So this one's a little bit different. So if you put them together, you get something that looks like this. So here's the 2 carbons and bonded to hydrogens, and here is the double bond. Now you might look at this and say 1, 2, 3, but the sigma bond is the first, and then this is representing a single pi bond. So there's only one pi bond there. So it overlaps it overlaps above and below anytime you have a double bond. Again, for a Lewis structure, it's nice and pretty to just draw 2 parallel lines, but it looks a little bit more complicated here. Now, again, with single bonds, you have this freedom of rotation. So probably the most significant difference when you introduce a double bond is it prevents this rotation and it locks it into a specific geometry. You do not have rotational motion when there is a double bond. So now, similar to on the previous slide, here is a two carbon molecules with fluorine. And if these were single bonds on the previous side, I said, oh, they're actually the same thing because it can rotate. But when they're double bonds, they're locked. It would take a chemical reaction to convert this isomer to this isomer. And so that's not going to happen spontaneously. So these are 2 different isomers, whereas with single bonds, it was actually the same thing. Here is a nice video link about greenhouse gases that talks about some of these rotations. You should definitely watch it, and you'll hurt my feelings if you don't watch it. If you have a triple bond, again, it starts off with a sigma directly in between, and then there's a pi bond. Above and below is the electron density. And then there is a second pi bond, but just 90 degrees, so perpendicular from the first. So now if we pack all this together, we get this weird hot dog looking thing. So there's the sigma bond in the middle. There's 1 pi bond above and below. There's a second pi bond to the left and to the right. And so overall, the red is representing the electron density, just a whole bunch of electron density being represented in the middle. So again, we don't have quadruple bonds because there's just not really any room left for electrons to get paired up. So on your homework, you might see some questions that look like this. How many pi bonds or how many sigma bonds? Now let me first mention that there's some shorthand notation. So CH3, this is the same as, hold on, let me do a thing real quick. There we go. So CH3 right there is, it's a short way to just not show every single bond, but you can know that there's, if you see C next to H, it's a hydrogen. So we also have some nitrogen, and here's carbon with 2 single bonds to hydrogen, etc. So if we want to know how many pi bonds, we need to know first that all of the single bonds have 0 pi bonds. They're only sigma. And a double bond will have 1 pi and 1 sigma, and a triple bond will have 2 pi bonds. So where you see double bonds, there's 1 sigma and 1 pi. Here's 1 sigma and 1 pi. And here's 1 sigma and 2 pi. So to answer this question, there are 4 pi bonds. Again, I want you to know that wherever you have pi bonds, it locks the geometry and there is no rotation. Whereas, so this bond here could rotate, this bond here will not. So to finish up the chapter, I want to talk a little bit about polymers. Polymers are something you use every single day. They're makeup components of your cell phone, your laptop, your clothes, even your car, computers. The world would be a very, very, very different place if we didn't have plastics. And they were developed within the last 100 years. And pretty much, if you go back 60 years ago, where everything was packaged by either glass or metal, aluminum, tin, now so much of it we use plastics in its place for its plasticity, its ability to be molded, but then also its relative strength, and and how lightweight it can be. So again, the word polymer, poly means many, and mer, we talked about isomers, have the same, iso is same, mer is unit. Well, polymer is just a chemical made up of a large repeating number of units. Now, there's already lots and lots and lots of natural polymers. The most common that I like to talk about are proteins. So from Mr. Pate's class, you could probably tell me what proteins do. Okay, say it. Yep, they do everything, and they are built upon a chain of amino acids. So amino acids are much smaller chemicals, but when you link one to another, 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 you get a protein. Much in the same way, you have DNA. So it's a long, another linear molecule where you have nucleic acids, your adenine and thymine and guanine and cytosine, but you link them together again and again and again, and you have a strand of DNA. But again, those are polymers. Sugars, if you're writing on paper, or again, looking at some tree bark or other plants, cellulose is just a complex form of carbohydrate. So technically you can take a piece of paper and turn it into sugar if you get the right enzymes like amylase. Now you wouldn't want to eat paper on its own, and it doesn't taste sweet, but we could break it down to single units of glucose and fructose, and that's what we normally think of as normal sugars. And then there's other ones like natural rubber. There's a nice protein and DNA bonded together, but what they all have in common is they have a single units. The units can vary, but they repeat over and over. And we're talking hundreds, thousands, tens of thousands at a time. Now, there's a lot of synthetic plastics, polymers. Again, that's probably the most common form, non-biological. When we think of plastics, they're going to be polymers. So something like polyethylene or polypropylene, polyvinyl chloride, nylon, Teflon. You've probably heard of some of these, Kevlar. Again, each one of them are made by taking a smaller chemical and somehow linking it again over and over and over and over and over. So I want to show you what that reaction sort of looks like. And so this is called a polymerization, and it is a addition reaction. And when you see the word addition, you can kind of think of you're adding on. So we're going to have, in this case, ethylene. Here's ethylene. Ethylene has this double bond, and that double bond makes it a little bit more reactive than single bond. Now, R stands for and it has one dot, that stands for a free radical. Now, one way you can introduce lots of different types of free radicals. One way you can do it is by taking something like chlorine gas and firing ultraviolet light at it, and it will cause a free radical to form. But free radicals are very reactive. And so this lone pair electron, it doesn't like to stay alone. So it's going to come over here and steal an electron. And in the process, it's going to form a covalent bond, but then this other electron gets kicked out. And so we end up with this. So now we have our free radical linked to ethylene, but the double bond is gone. Now it's a single bond, and that has a free radical. And so if you could imagine, there is more ethylene present. So here's another molecule of ethylene. So with this free radical, it steals an electron from that double bond, makes a covalent bond, and extends the chain. And so this can go on for literally hundreds, thousands, tens of thousands until eventually the ethylene runs out. And so when you're done, you get not just not this ethylene with 2 carbons, but a polymer where this chain can be hundreds of thousands of units long. And so once that happens, we don't really give it a formula like C7H20 whatever. Instead, we just say polyethylene. And so here, plastic bags, for lunch bags, that's just standard polyethylene. Now, there are a lot of different types of plastics, and the way you get different plastics is by changing the monomer. So if polymer is the whole thing together, the monomer is what was getting linked. So here's polyethylene has a monomer of ethylene. But if you want to make polypropylene, here's propylene. It's got an extra carbon. So when you link them together, notice it's still a long strand of carbon, but now you have these extra carbon groups, and it gives it different properties. So most water bottles, soda bottles, they're made of a lot of them polypropylene. If you substitute a chlorine, you get chloroethylene. And if you polymerize it, you get polyvinyl chloride. And so a lot of plumbing pipes and other, it has a whole lot of utility, a lot of uses. Now, if you take, instead of a chlorine, this is a benzene ring. This whole thing's called styrene. But then if you polymerize that, you get polystyrene. And if you make a foam of it, you get styrofoam. So something we use for beverages and cheap, as a cheap container. Again, last example, even though there's dozens and dozens of these, tetrafluoroethylene. So it has 4 fluorines, and when you polymerize it, you get PTFE, so polytetrafluoroethylene, which you might know as Teflon. There's a fun video down here you should definitely click and watch about why Teflon is so awesome. But again, for different reasons, or for different utility, different needs, we have all sorts of different plastics. Here's a nice infographic. I should put an orange box. You do not have to know all the different types, but it's just showing many of the different types. If you've ever seen these numbers at the bottom, 1, 2, 3, 4, 5, 6, 7, it tells you about what type of plastic it is, and then allows you to know, can you recycle it or not? Because some can be recycled, others are not. Here's a fun video about that. Legos, great example. My 6-year-old loves Legos right now. He's actually kind of transitioning into Minecraft, and it's kind of hard to get him to stop talking about Minecraft right now. Anyway, Legos are an example of a copolymer. So if you have polystyrene or polyvinyl chloride, those have one monomer, but you can then mix multiple types together to get a copolymer. Again, nitrile gloves have, or acrylonitrile butadiene. So Legos have 3 monomers: acrylonitrile, 1,3-butadiene, and styrene. And together they give them the favorable properties that they like. And you can read all this for fun facts. Again, things like plastic gloves, tires, even bubblegum are all generally synthetic plastics. And again, a lot of them are copolymers. So that is it. That is the end of this chapter. There's a whole bunch of stuff to study. Here's a fantastic musical rendition of a song you've probably heard of, but it's a parody based on chemical bonding, and you should watch it. But yeah, this video serves as your content for both Thursday and Friday. Where really you could watch it all Thursday, and then I'm going to call Friday be work on the homework day and get that done. So on Monday, plan for a quiz to be taken at home, and then Tuesday I'll be sending out quiz keys and stuff to look over. I'll be available for Google Hangout, or I can answer all sorts of emails. And then Wednesday we'll try our first test. We'll see how that goes. But I hope you have an absolutely fantastic day, and you take care.